Okay, today I will solve the problem 9.16 and problem 9.17. And for problem 9.16, a thin linear antenna of length d is excited in such a way that a sinusoidal current makes a full wavelength of oscillation as shown in the figure. And the problem A, calculate the exactly the power radiated per unit solid angle and plot the angular distribution of radiation. And problem B is determine the total power radiated and find a numerical value for the radiation resistance. And this is the configuration of these problems. The linear antenna is lying in the z-axis, and the current is oscillate in the full length of this antenna, where our coordinate is setting the center of the antenna is the origin. So to get the vector potential, we first write down the current density J with the harmonic time dependence here. The current density J is equal to I sine kz delta x delta y and theta d divided by 2 minus absolute value of z in the z direction. Because our antenna is lying in the z-axis, so we will get the delta x, Dirac delta x, and Dirac delta y. And for the finite size of our antenna, the theta function will give us the unit when the argument is greater than 0, and give us 0 if the argument is smaller than 0. Thus, our theta function will equal to 1 when our z coordinate is smaller than d divided by 2. And the I is the peak value of the current, and this sine kz is the sinusoidal oscillation in our antenna, where with the following constraint, the kd is equal to 2 pi. The vector potential A in the radiation zone is given by equation 9.8. A is equal to mu naught divided by 4 pi times exponential IKR divided by R, and times the integration current density times exponential minus IK R hat times R prime in the z prime directions, where the prime is the source coordinate and the unprime symbol is the observation coordinate. And after we expand our current density and take the integration for the x and y positions, finally we will get that our vector potential is the constant times the exponential IKR divided by R times the z integration, the sine kz prime times exponential minus kz prime cosine theta, where the theta is the angle between the z directions of the in the z directions of our coordinates and the observer's vector. And since the real part of the integration is an odd function here, so the integral will vanish. We only need to calculate the imaginary part. So the vector potential is equal to the I here is come from the exponential's imaginary part with the sine kz prime cosine theta. And after we change the integral region from the minus d divided by 2 to d divided by 2. We change this region to 0 to d divided by 2. since the function is an even function. And after we integrate, take the upper and lower limit, we get that our vector potential is equal to the I mu 0 divided by 2 pi times the current times exponential IKR divided by R times the sine pi cosine theta divided by sine squared theta. And in the radiation zone, the magnetic field is H equal to IK divided by mu naught times the R hat cross product vector potential. And since R hat cross our vector potential only have a z direction here, so the R hat cross z hat will give us a minus sine theta phi hat. So our magnetic field now is the minus phi hat times the current divided by 2 pi times exponential IKR divided by R times sine pi cosine theta divided by sine theta. And in the radiation zone, the electric field is just directly related to the magnetic field in the following equations. E is equal to the Z naught magnetic field cross product the H hat. And the radiation power per solid angle is given by the formula dp d omega is equal to the Z naught times R squared divided by 2 times the magnitude of magnetic field, the magnitude of magnetic field squared, and is equal to this. And we take a plot in the xz plane since our system have azimuthal symmetry. Thus, our angular distribution is independent of the phi directions. So I pick a particular phi here. The upper and the lower coordinate is the positive x and minus s. The right is positive z, and the left hand is the minus z. And the total power and the radiation resistance is calculated in the following form. The P is the integration of the power per solid angle and integrate the whole solid angle. And the later one, this integration here is a spatial function which will give us 1/2 times gamma plus log 4 pi minus sine function 4 pi, which is about 1.557, where the sine function is a spatial function here. This can written in the integration form, and the gamma is equal to the 0.577, which is so-called Euler-Mascheroni constant. And the total power is given by these expressions after we put our numerical value. And the radiation resistance is given by the formula P is equal to 1/2 times I squared times R radiation. So the radiation resistance is equal to Z naught divided by 2 pi times 1.557, which is about 93.4 ohm. And for the problem 9.17, treat the linear antenna of problem 9.16 by the multiple expansion method. And problem A, calculate the multiple moment, electric dipole, magnetic dipole, and electric quadrupole exactly and in the long wavelength limit. And B, compare the shape of angular distribution of radiation power for the lowest non-vanishing multiple with the exact distribution of problem 9.16. And problem C, determine the total power radiated for the lowest multiple and the corresponding radiation resistance using both multiple moments from part A and compare with the problem 9.16b. Is there a paradox here? So to calculate the multiple moment, we first need to calculate the charge density. From the problem 9.16, we have shown that the current density J can written in the Dirac delta function and the state function and sin kz. The charge density rho can be calculated from the continuity equation. Rho is equal to the divergent state divided by I omega. And since our J only have the z direction dependence, so the divergence will become the z direction derivative. And after we calculate the derivative, we get that our rho is equal to minus I divided by C times I times current times cosine kz delta x delta y and theta div divided by 2 minus absolute value of z, where we use the dispersion relation ck equal to omega. And since originally the derivative of current density will need to calculate the derivative of the theta function, but since this derivative of theta function will give us a Dirac delta function, which will take value at the z equal to the positive or negative d divided by 2, and since the sign of positive or the function sin kd divided by 2 is equal to the sign positive or negative pi, which is give us 0. So this contribution is vanished in the charge distributions. Thus, the charge distribution only have the cosine kz terms without the derivative of the theta function. And to calculate the electric dipole moment, the electric dipole moment from the definition is P equal to the position vector times charge density and take the integration. And since we have the Dirac delta x and Dirac delta y, the position vector only have a contribution in the z component. So the integration, we only need to calculate the z integration. And since the z cosine kz is a odd function, so this integration will give us 0. Thus, this system don't have any electric dipole moment here. And for the magnetic dipole moment, m is defined by 1/2 times the position vector r cross the current density and take the integrations. However, since again we have a Dirac delta x and Dirac delta y, the position vector only take value at the z component, but the z vector and the z unit vector cross the z unit vector is 0. So this system also don't have any magnetic dipole moment. The next order is the electric quadrupole moment. The electric quadrupole moment is defined in the following way. Qij is equal to the integration of the 3xi(xj) minus r squared delta ij times charge density. And since the Dirac delta x and Dirac delta y, the position coordinate is only take value at the z component. So the only non-vanishing term and the only non-vanishing moment are Q33 and Q11 and Q22 with the relation Q33 is equal to minus 2 Q11 is equal to minus 2 Q22. And the integration from, and after we take the integration, we will get that the quadrupole moment is equal to the 8 pi I divided by ck cubic times the current. And in the long wavelength limit, which means kd goes to 0, both the electric and magnetic dipole moments are vanished because of the same argument from the symmetry z equals z and minus z. And from the symmetry, we can exchange the z to the minus z, and this system is not changed. The electric quadrupole, so the lowest non-vanished multiple moment is the electric quadrupole moment, and because in the long wavelength limit, the cosine kz in our integral can replace to the unity because the z is bounded by the current size here, so the cosine kz is just about can take the value equal to the cosine kd, and kd is goes to 0, so the cosine here is almost equal to the cosine 0, which is equal to 1. And after the calculation, we find that the quadrupole moment is depend on the kd's cubic, and since our kd is goes to 0, so the quadrupole moment is almost vanished. And this expression is greatly underestimate the actual quadrupole moment, and the reason is because the wavelength of the exact expansion is confined by the size of the current source. So the lambda, the wavelength, is at most equal to the size of wavelength. The wavelength can greater than d. Thus, the long wavelength limit kd is inconsistent with this system's configuration because kd at least is equal to 2 pi. And we use the result for angular distributions. We use the result in the multiple expansions, in the exact multiple expansions. The angular distribution of quadrupole radiation power is given by the equation 9.51. The angular distribution dp d omega is equal to the constant times q naught square times sine square theta cosine square theta, and the q naught is equal to the qc3. And after we take the value of qc3 into our expression, the angular distribution is equal to z naught times I squared divided by a times sine square theta cosine square theta. And to compare the result our exact calculation in problem 9.16, we plot the angular distributions in the unit z naught times I squared divided by a pi squared. And one can see that the exact solution, which is I use the blue color here, is smaller, have a smaller magnitude of power than the quadrupole moment, which is used in the orange color or maybe red color here. But the problem B only want us to compare their shapes, so we can normalize both solutions into the same magnitude, and we can see that their shape is almost the same. The overlapping is and the exact result is almost like a quadrupole radiation behavior. The total power from the quadrupole moment is calculated in the following formula, and after we take the integrations, the P is equal to the Z naught times I squared times pi divided by 15th, and the corresponding radiation resistance is equal to the 2 pi divided by 15 times Z naught, which is about 158 ohm. And this result is much larger than the exact calculation. So from the calculation in the quadrupole radiation resistance, we find that the quadruple radiation power is greater than the exact one, and it seems like a paradox here, because the power radiation can only increase if we add the higher multiple moment in our calculations. So, however, this is not a paradox, and the reason is given in the following. The reason of this phenomenon is the destructive interference from the higher order terms in the expansion of the x minus s prime absolute value in the equation 9.7. If we want to get a true power of the quadruple radiation fields, we should use the equation 9.155 and 9.167 for the radiation multiple, and instead of equation 9.51 and 9.52, which is calculated in the long wavelength limit of the expansion s minus s prime absolute value, to include the quadruple radiation effect from a higher order terms. The total radiation power P can express in the following form: Z naught divided by 2k squared times the sum over all mode, the electric multiple coefficients squared plus the magnetic multiple coefficients squared. And the electric quadruple coefficient is given by the equation 9.184 with the even L. The coefficient AEL0 is equal to this, where the JL is the spherical Bessel functions, and KD is equal to 2 pi. And in particular, for L equal to 2, the AE20 is equal to k divided by 2 times square root of 13 divided by pi cubic times the current. So the angular distribution dp d omega is equal to Z naught times I squared times 225 divided by 32 times pi to the power 4 times sine squared theta cosine squared theta. And we plot the angular distribution again in the unit of Z naught times I squared divided by A pi squared. And we can see, without any normalization, the exact one and the quadruple one is almost the same, just a little difference in the angular direction, in directions. And the total power we get in this angular distribution is equal to the Z naught times I squared times 15 divided by 4 pi cubic, and the corresponding radiation resistance is equal to the Z naught times 15 divided by 2 pi cubic, which is equal to 91.1 ohm. And this result is only 2% less than the exact one, which means the quadruple moment is actually the dominant one in these systems. But in order to calculate this result, we need to add the higher order terms in the s minus s prime expansions.